I'll discuss Cantor theorem, which is a generalized version of Cantor's diagonal argument. Cantor theorem states that for any set A, the set of all subsets of A, including the empty set, the power set of A, written as PA, has a strictly greater cardinality than A itself. For finite sets, Cantor theorem is true by simple enumeration of the number of subsets because 2 to the power of I is larger than I for any natural number I. Because Cantor theorem shows that there is no bijection between any set A and the power set of A, he argued that the size of the power set of natural numbers Pn, which is 2 to the power of aleph null, should be strictly larger than the size of the set of natural numbers, which is aleph null. The theorem is, let function f be a map from set A to its power set PA, then the function A to PA is not surjective. Thus, card PA is larger than card A for any set A. The proof is this. Consider the set B where x is an element of A and x is not an element of fx. Suppose there exists epsilon, which is an element of A such that f epsilon equals B. Then it implies the following contradiction. If epsilon is an element of f epsilon, then epsilon is an element of B by assumption that f epsilon equals B. If epsilon is an element of B, then epsilon is not an element of f epsilon by definition of B. Therefore, this is a contradiction. Thus, f cannot be surjective. Therefore, card PA is larger than card A. The concept of the set B is rather abstract. Thus, I'll show B more visually. The set B, whose element x is not an element of fx, is called Cantor's diagonal set, and you'll see why. Suppose you have a list of fi, which are subsets of natural numbers. f1 is an empty set, f2 is a set of all natural numbers, f3 even numbers, f4 odd numbers, ... Then make a subset B by having x that is not an element in fx, which is the definition of set B. Thus, because there is no 1 as an element in f1, 1 is included as an element in B. And there is 2 as an element in f2. Thus, 2 is not included as an element in B. There is no 3 as an element in f3. Thus, 3 is included as an element in B. Then, B is different from any fi in the list. Then, you note the similarity between the Cantor's diagonal set B in the Cantor theorem and E sub 0 in the Cantor's diagonal argument, which can be seen more clearly by changing the presence or absence of each element in the set as 1 or 0. Then fi becomes a list of binary digits, and B becomes a number of binary digits, ith digit complementary to the ith digit in the set fi. In other words, Cantor's theorem is another expression of CDA. Cantor theorem generates many paradoxes. Define path number 1 as card Pn, which is 2 to the power of Aleph null. Define bet I plus 1 as card P bet I, which is 2 to the power of bet I for any natural number I. Then bet 2 is larger than bet 1, and bet I plus 1 is larger than bet I. Thus, Aleph null is smaller than bet 1 is smaller than bet 2, ... leading to the conclusion that there are many sizes of infinity, and there is no greatest infinite cardinality. The cardinality of the number of the infinite cardinality is infinite. Please send critical comments to this address. Thank you very much.